Now we're going to find some eigenvectors. So actually, let's start with some lambdas. Let lambda equal 2 and 3. That means that our characteristic polynomial needs to have roots 2 and 3, so lambda minus 2 times lambda minus 3 is 0. That multiplies out to this polynomial, and we can read right off of it that the trace of our matrix needs to be 5, and the determinant of our matrix needs to be 6, and we're going to actually make a matrix, construct a matrix that works. So for the trace to be 5, let's just put 1 and 4 on the diagonal. We could have put 0 and 5 or 2 and 3, or we could have put non-integers, but we chose 1 and 4. And then our determinant is 1 times 4 minus b times c, so that's 4 minus bc, and it needs to be set equal to 6. And so that means that bc is going to be negative 2, and so we need to choose b and c, so their product is negative 2. And that will ensure that we've constructed a matrix that has these particular eigenvalues. And so we choose 2 and negative 1, and we know that the eigenvalues are 2 and 3. And we're asking the question, what is the eigenvector where 1, 2, negative 1, 4 times that vector is equal to 2 times that vector? To do this, we start with the matrix 1 minus lambda, 2, negative 1, 4 minus lambda, and lambda was 2. So that matrix simplifies to negative 1, 2, negative 1, 2, and we can see that this is very much a singular matrix, and what we're wondering about is what vector, if it were placed right here, would yield a 0. And so if v is equal to, let's say, u little v, then we want to be able to put uv right here and get negative u plus 2v to be 0. And if we do that, then both the first row times uv and the second row times uv will yield zeros, and so that will be an eigenvector. And so we just need some vector that satisfies negative u plus 2v equals 0. And so that tells us that 2v is equal to u. So if we choose some number for v, let's just choose 1, then we should choose twice that number for u, which will be 2. So an eigenvector is 2, 1. Of course, any multiple of this vector is also an eigenvector. However, 2, 1 is a relatively nice way to represent this vector direction, and that vector direction is going over 1 and wait a sec, going over 2 and up 1, so it's this direction is the eigen direction associated with the eigenvalue 2. So now we need to do this process again. For the other eigenvalue, we plug it into 1 minus lambda, 2, negative 1, 4 minus lambda, and we get negative 2, 2, negative 1, 1. This is also very clearly a singular matrix. 2 times this first row is this second row. And so we need uv to satisfy negative u plus v is equal to 0. And so that just means u equals v, and our eigenvector is the 1, 1 direction. And now we check both of these eigenvectors. So if we take our original matrix 1, 2, negative 1, 4, and we multiply it by the vector 1, 1, we get back 3, 3, which is equal to 3 times that vector direction. Okay, indeed, there's our eigenvalue, there's our eigenvector, and we also plug in 2, 1. This matrix times 2, 1 yields 4, 2, which is equal to 2 times 2, 1. There's our eigenvalue, there's our eigenvector, and so checking in this way, we see that indeed we found the correct eigenvectors for these two eigenvalues.